February 1943. A Grumman Wildcat returns to USS Ranger with a hole the size of a man's torso punched through its starboard wing. The fabric is shredded. The ribs are splintered. Command wants it scrapped. A 34-year-old machinist's mate named Frank Walters tells them he can fix it with sheet aluminum and rivets. They laugh. He does it anyway. 3 weeks later, that same wing survives a near-vertical dive through flak over Casablanca at 320 miles per hour. The North Atlantic in winter is a study in gray. Gray sea, gray sky, gray steel deck heaving beneath boots that never find sure footing. Carrier duty in early 1943 means cold that seeps through wool, through skin, into bone. It means aircraft that corrode faster than they can be maintained. It means pilots who need their planes ready yesterday and mechanics who work miracles with nothing. The USS Ranger is an older ship. Commissioned in 1934, she is smaller and slower than the Essex-class carriers that will dominate the later war. Her aircraft complement is modest. Her mission is unglamorous. Convoy escort, anti-submarine patrol, transport duty between Norfolk and North Africa. But her deck crews are as skilled as any in the fleet. They know how to stretch resources. They know how to improvise. On the flight deck, the sound is constant. Engines turning over, propellers biting cold air. The clang of wrenches and the hiss of pneumatic tools. Below deck, in the machine shop and repair bay, the noise is different, more intimate, more deliberate. The rasp of files, the whine of drill presses, the hammer-tap rhythm of rivet guns. This is where Frank Walters works. He is a machinist's mate first class, not an officer, not an engineer, not a designer. Just a man who understands metal the way a surgeon understands tissue. He knows how it bends, how it fails, how it holds. He has spent 20 years in machine shops, civilian and military, learning the grammar of stress and tolerance. He does not speak much. He listens to the metal. The Wildcat that lands on February 7th is a mess. Pilot barely kept it airborne. A German FW-190 caught him during a patrol sweep off the Moroccan coast. Cannon rounds stitched across the right wing. One punched clean through, tearing fabric and splintering the wooden ribs beneath. The damage is structural. The wing flexes wrong. Command tags it for depot-level repair, meaning it will be offloaded, sent stateside, and replaced. Walters looks at it differently. He walks around the aircraft slowly, runs his hand along the torn fabric, peers into the wound. The aluminum spar is intact. The main load-bearing structure is undamaged. Only the ribs and the fabric skin are compromised. In his mind, it is not a totaled wing. It is a repair problem, a solvable one. He tells the maintenance officer he can patch it. The officer looks at him like he suggested welding the wing back together with spit. Wildcats use fabric-covered wings. You do not just slap metal over fabric. The aerodynamics will be wrong. The weight distribution will be off. The flex characteristics will change. Fabric and metal expand at different rates. The patch will crack. The wing will fail. Walters listens, nods. Then he explains. The aluminum patch will be bonded directly to the spar and ribs. It will not replace the fabric. It will reinforce the damaged section. He will use thin sheet stock, not heavy plate. He will contour it to match the airfoil. He will rivet it in place with aircraft-grade fasteners, spaced close enough to distribute load, but not so close that they weaken the surrounding structure. The patch will be stronger than the original fabric. It will not flex more. It will flex less. That is the point. The officer is unconvinced, but the wing is already written off. If Walters wants to waste his time, fine. Just do not expect it to fly. Walters does not expect. He calculates, if this story matters to you, tap, like, and subscribe. Frank Walters was born in 1909 in Erie, Pennsylvania. His father worked the rail yards. His uncle ran a machine shop that serviced locomotives. Walters grew up around metal, hot, cold, cast, forged, welded, riveted. He learned young that metal has memory. It remembers how it was formed, how it was treated, how it was stressed. Push it too far and it fails. Respect its limits and it endures. He quit school at 16 to work full-time in his uncle's shop. By 18, he could operate a lathe, a mill, and a drill press with the precision of a journeyman twice his age. By 20, he was running jobs on his own, custom parts, one-off repairs, impossible tolerances. He did not design, he executed. But execution required understanding, and understanding required curiosity. He read engineering manuals at night, not for credentials, for comprehension. He wanted to know why a bolt sheared at a certain torque, why a casting cracked in cold weather, why one alloy held under fatigue and another did not. He did not pursue theory for its own sake. He pursued it because it made him better at solving real problems. When the Depression hit, the shop nearly folded. Walters took whatever work he could find, tool and die, automotive repair, fabrication. In 1935, he enlisted in the Navy. The pay was steady. The work was similar, and the machines were more interesting. Aircraft were the new frontier, lighter, faster, more demanding, tolerances measured in thousandths of an inch, materials pushed to their limits. He served aboard USS Lexington as a machinist's mate, 3rd class. Then, aboard USS Saratoga, he was promoted twice. He earned a reputation as the man who could fix what others could not because he was smarter, because he looked closer. He asked better questions, he tested assumptions. By the time he transferred to USS Ranger in 1942, he was a first-class petty officer, senior enough to have authority in the shop, junior enough to still get his hands dirty. He preferred it that way. Leadership meant paperwork. He wanted tools. His crewmates called him Frank the Fix, not with irony, with respect. He did not boast. He did not grandstand. He just solved problems quietly and moved on to the next one. If a valve body cracked, he machined a new one. If a landing gear strut bent, he straightened it. If a propeller blade nicked, he filed it true. He was not a maverick. He followed procedure when procedure worked. But he understood something many officers did not. Procedure was a guideline written for the average case. War produced edge cases, and edge cases required judgment. The Wildcat wing was an edge case. The Grumman F-4F Wildcat is not the fastest fighter in the fleet. It is not the most maneuverable. It is not the longest ranged, but it is tough. Grumman builds aircraft like tanks, armor plate, self-sealing fuel tanks, robust structure. The Wildcat can take punishment and keep flying. Pilots trust it, maintainers respect it, but toughness has limits. By early 1943, the Wildcat is outclassed in the Pacific. The Japanese Zero is faster, climbs better, turns tighter. American pilots survive through tactics, dive and zoom, mutual support, disciplined gunnery. They do not dogfight. They do not turn. They rely on the Wildcat's durability and hit-and-run speed. In the Atlantic and Mediterranean, the threat is different. German fighters, Bf-109s and FW-190s, are heavily armed and flown by experienced pilots. Encounters are brief and brutal. A single cannon hit can cripple an aircraft. Damage accumulates faster than repair capacity can manage. Carriers operating in these theaters face a chronic problem: aircraft availability. Planes are damaged faster than they can be fixed. Spare parts are scarce. Replacement aircraft take weeks to arrive. Every plane that can be returned to service matters. Every plane written off is a gap in the air wing. But Navy doctrine is rigid. Battle damage is categorized by severity. Minor damage, bullet holes, small tears, can be patched aboard ship. Major damage, structural failure, control surface loss, engine damage, requires depot-level repair. The damaged Wildcat falls into the latter category. The wing structure is compromised. Doctrine says it cannot be safely repaired at sea. Doctrine is written for good reason. Field repairs that fail in flight kill pilots. Improvised patches that do not account for aerodynamic loads can cause catastrophic failure. The Navy has seen it happen. A poorly executed repair is worse than no repair at all. Better to ground the aircraft than risk a pilot's life, but doctrine assumes you have replacement aircraft. USS Ranger does not. The damaged Wildcat is one of 18 operational fighters aboard. Lose one, and the air group is stretched thinner. Patrols get longer, combat air patrol gets weaker, fatigue accumulates. The maintenance officer knows this, so does the air group commander, so does the captain. They want the plane back, but they will not cut corners. They will not approve a repair that might kill someone. Walters understands this. He does not argue, he simply asks for permission to try. If the patch fails, the plane is already grounded. Nothing is lost. If it works, the air group gains an aircraft. The risk is his time and the ship's materials. The reward is operational readiness. The maintenance officer gives him 48 hours. If the repair looks sound, engineering will inspect it. If it passes inspection, they will consider a test flight. If it fails at any stage, the wing is scrapped. Walters nods. He does not need 48 hours. He needs 12. He begins by mapping the damage. Not by eye, by measurement. He uses calipers, straight edges, and feeler gauges to measure the distortion in the wing ribs. He traces the tear in the fabric. He checks the alignment of the spar. He documents everything in a pocket notebook. Dimensions, angles, distances. The main spar is undamaged. That is critical. The spar carries the primary flight loads, bending moment and shear stress from lift and maneuver. If the spar were cracked, the wing would be unsalvageable, but it is intact. The ribs, thin, stamped aluminum formers that give the wing its airfoil shape, are bent and torn. 3 of them are compromised. The fabric covering is shredded across a 2-foot span. Walters calculates the load path. In normal flight, the fabric skin does not carry much structural load. It provides aerodynamic shape and torsional stiffness. But in high-speed maneuvers, especially dives and hard turns, the skin carries significant shear. A fabric patch will not hold. Fabric fatigues, fabric stretches, fabric tears, metal will not. He selects a sheet of Neo 25-inch aluminum, thin enough to form without specialized tools, thick enough to carry shear load. He cuts a rough blank slightly larger than the damaged area. Then he begins shaping it. This is the part that cannot be rushed. The wing has a compound curve. Camber along the chord, twist along the span. The patch must conform to that curve without buckling or wrinkling. Walters works the metal slowly, using a sandbag and a mallet to form it incrementally. He checks the fit every few minutes, trims, reforms, rechecks. After 6 hours, the patch fits like skin. He drills rivet holes, carefully, spacing them to distribute the load without creating stress concentrations. He deburrs each hole by hand, cleans the surfaces, applies a thin layer of zinc chromate primer to prevent galvanic corrosion between the aluminum patch and the steel fasteners. Then he begins riveting. Each rivet must be set with the correct pressure. Too loose, and it will not clamp. Too tight, and it will crush the surrounding metal. Walters sets each one by feel. Tap, tap, tap. He listens to the pitch of the hammer, feels the resistance. When the rivet head is flush and the shank is tight, he moves to the next. It takes 3 hours to set 42 rivets. By the time he finishes, it is 0300. The hangar deck is quiet. Most of the crew is asleep. Walters steps back and examines the wing. The patch is smooth. The contour is clean. The fasteners are uniform. It looks factory, but looking right is not the same as being right. He runs his hand along the surface, feels for discontinuities, presses gently on the patch to check for flex. It moves, slightly, but no more than the surrounding structure. That is good. If it were too stiff, it would create a hard point. If it were too flexible, it would not carry load. He checks the alignment of the trailing edge, measures the chord at 3 stations, confirms the airfoil symmetry. Everything is within tolerance. He writes a 1-page report, lists the materials used, describes the repair process, notes the measured dimensions before and after, signs it, leaves it on the maintenance officer's desk. Then he goes to his rack and sleeps for 4 hours. The maintenance officer reads the report at 0700. He is skeptical, but the work is done, and the documentation is thorough. He walks down to the hangar deck with the ship's engineering officer and a structural inspector. They examine the wing for 30 minutes. The inspector taps the patch with a coin, listens to the ring, checks the rivet spacing with a ruler, runs a feeler gauge along the seams, pulls on the trailing edge to test for play. He does not speak, just nods occasionally. Finally, he looks at the maintenance officer. The repair is sound. Structurally, the wing is airworthy, but aerodynamically it is an unknown. The patch changes the surface. It adds weight. Not much, maybe 5 pounds, but enough to shift the center of gravity slightly. It might create turbulence at the boundary layer. It might affect stall characteristics. There is no way to know without flight testing. The maintenance officer asks if it is safe to test. The inspector pauses, then says yes, with limits. No aerobatics, no hard maneuvering. Straight and level flight at moderate speed. If the wing behaves normally, they can expand the envelope. If it does not, they land immediately. The Air Group commander assigns the test flight to Lieutenant Paul Deckard. Deckard is not a test pilot. He is a section leader, experienced, steady, not prone to heroics. He has 300 hours in the Wildcat. He knows what normal feels like. He briefs with Walters beforehand. Wants to understand the repair. Walters walks him through it, explains the load path, shows him the rivet pattern, tells him what to watch for: vibration, unusual drag, control flutter. Deckard listens, asks good questions. Then he suits up. The flight is scheduled for 1400 hours. Weather is clear. Sea state is calm. The deck crew positions the Wildcat on the catapult. Deckard climbs in, runs the pre-flight checklist. Engines start. Instruments green. Control check. Everything normal. The catapult fires. The Wildcat leaps forward and climbs away from the ship. Deckard holds a shallow climb to 5,000 feet, levels off, trims the aircraft, checks the wings visually. No deformation, no flutter. He banks gently left, then right. The controls feel normal. No unusual drag, no asymmetry. He reports over the radio. All normal so far. He flies straight and level for 10 minutes, varies speed from 120 knots to 180 knots. The wing behaves identically to the undamaged side. No vibration, no buffet. He asks for permission to test a steeper bank. Maintenance approves. He rolls into a 60-degree turn, pulls 3 Gs, holds it through 360 degrees. The wing holds. The patch does not buckle. He levels off. Reports again. Still normal. The Air Group commander considers. They need to know if the wing will hold under combat loads, but they cannot test that safely at altitude. If something fails, Deckard might not recover. The smart move is to call it good enough and impose operational limits on the aircraft, no aerobatics, no hard pulls. But Deckard offers an alternative. Let him fly one practice dive, not a vertical dive. A 45-degree attack run like he would use on a ground target. That will load the wing with 4 to 5 Gs, real combat stress. If the patch holds, the aircraft is fully mission capable. If it does not, he will still have altitude to recover. The maintenance officer looks at the engineering officer. They both look at the captain over the radio circuit. The captain approves the test. Deckard climbs to 8,000 feet. He lines up on a heading that will take him clear of the ship. He throttles back, extends dive brakes, noses over. The Wildcat accelerates 180 knots, 200, 220. The airframe shudders slightly. Normal compressibility effects at high speed. The altimeter unwinds. 7,000 feet. 6,000. He steepens the dive to 50 degrees. Speed climbs to 240 knots. At 5,000 feet, he pulls. The G-forces slam him into the seat. The airframe groans. The wings flex upward, visible from the cockpit. He keeps the pull steady. 4 Gs, 5 Gs. The nose tracks through the horizon. He levels off at 3,000 feet. The wing is intact. No deformation, no cracks, no popped rivets. Deckard keys the radio. Patch is solid. Wing is good. He returns to the ship and lands without incident. Walters is on the deck when the plane traps. He does not approach, just watches from the catwalk as the plane director taxis the Wildcat to the line. When Deckard climbs out, he walks over to Walters, does not say much, just shakes his hand. The maintenance officer authorizes the Wildcat for full operational duty. The patched Wildcat flies 23 more combat sorties over the next 2 months. Convoy escort off the Azores, combat air patrol over Casablanca, ground attack missions in support of Operation Torch. The wing never fails, the patch never cracks. Other maintainers notice. By March, 2 more Wildcats with wing damage are repaired using Walters's method. By April, the technique has spread to USS Santee and USS Suwannee, escort carriers operating in the same theater. By June, it is documented in a Naval Aviation Maintenance Bulletin as an approved field repair for fabric-covered wings with rib damage and intact spars. The repair saves aircraft. That is measurable. But the larger impact is cultural. It demonstrates that field-level maintainers can solve problems that Doctrine says require depot-level facilities. It shows that improvisation, disciplined, documented, tested improvisation, can be as reliable as factory work. It validates the judgment of experienced petty officers who understand their aircraft better than the manuals do. This matters in a war where logistics is as critical as firepower. Every aircraft kept in service is one less aircraft that must be built, shipped, and delivered. Every day a plane stays operational is one more day it can fly missions. Multiply that across a fleet, and the effect is significant. By mid-1943, the Navy is producing detailed technical bulletins on field repair techniques. Some are born from necessity, some from ingenuity. Walters's metal wing patch is among them. It is not revolutionary, it is not glamorous, but it works. And in a war fought on thin margins, that is enough. Walters himself does not dwell on it. He moves on to the next problem: a cracked engine mount, a bent propeller hub, a fractured hydraulic line. The work never stops. The ship keeps moving. The aircraft keep flying. He is promoted to Chief Petty Officer in August 1943, transferred to USS Essex in 1944, serves through the end of the war, musters out in 1946 with a Navy Commendation Medal, awarded not for a single act, but for sustained excellence in keeping aircraft flying under difficult conditions. The citation does not mention the wing patch. It does not need to. The patch is part of a larger pattern, a habit of solving problems instead of accepting them, a refusal to let doctrine become dogma, a respect for the metal, the aircraft, and the pilots who depended on both. Frank Walters returned to Erie in 1946. He bought a small machine shop with his mustering out pay and a veteran's loan. He ran it for 30 years, doing the same kind of work he had always done: custom parts, repair jobs, impossible tolerances. He trained apprentices. He took on work other shops would not touch. He never advertised, did not need to. Word of mouth was enough. He rarely spoke about the war, not out of trauma, out of habit. The work had been the work. He had done what needed doing. So had everyone else. In 1978, a naval historian researching carrier maintenance in the Atlantic Theater came across the 1943 Maintenance Bulletin. The metal wing patch technique was attributed to a machinist's mate aboard USS Ranger. The historian tracked Walters down through Navy records, asked if he would be interviewed. Walters agreed. The interview was brief. He described the repair clearly and without embellishment, explained the reasoning, noted that the technique had been refined and improved by others, said he was glad it had been useful. The historian asked if he had been nervous when Lieutenant Deckard tested the wing. Walters thought about it, then said no. He had checked the math. He had done the work correctly. The patch would hold or it would not. Nervousness would not change that. The historian asked what he was most proud of from his service. Walters paused, then said he was proud that the pilots trusted the work, that they flew the aircraft he maintained without hesitation. That was the job, keeping them safe, keeping them flying. He died in 1991 at the age of 82. His obituary in the Erie Times-News mentioned his Navy service in a single sentence. It did not mention the wing patch. It did not mention the bulletin. It noted that he had run a respected machine shop and trained a generation of machinists. But in the archives of the Naval Aviation History Branch, the 1943 Maintenance Bulletin remains. It is a dry, technical document, 3 pages, diagrams, rivet spacing, material specifications, no drama, no flourish, just a solution to a problem. The patched Wildcat, Bureau number 2296, survived the war. It was retired in 1945 and eventually scrapped. No plaque, no museum. The aluminum patch that saved it was cut apart and melted down, its metal recycled into something else. But the idea endured. In every conflict since, maintainers have faced the same dilemma: how to keep aging aircraft flying when parts are scarce and time is short. They improvise, they adapt, they test, they document, they pass the knowledge on. Some of them know the story of Frank Walters, most do not, but they follow the same principle: respect the machine, understand the loads, do the work right, trust the math. It is not heroism in the traditional sense. There are no medals for riveting a patch, no songs written about machinists' mates. But there is a kind of honor in it, the honor of competence, of responsibility, of caring enough to get it right when lives depend on it. Frank Walters did not mock the men who doubted him. He did not prove them wrong out of pride. He simply understood something they did not yet see: that metal, properly applied, could do what fabric could not. He fixed the wing. The wing held. The pilot came home. That is the whole story, and it is enough.